Okay, so what I want to cover here it actually coincides quite well with this question 4 of tutorial 2. And we are told here component A is diffusing through your stagnant solvent towards a spherical particle, and it's consumed at a high rate. And we are given the total concentration and the diffusivity. And you'll see here the diffusivity it's written in a slightly different way, AE instead of the usual DAB. And that's because we think of this as an effective diffusivity. So we are usually thinking about the diffusivity of A against B, but of course the solvent as well is something that we should consider, the fact that A is diffusing against the solvent also. So to summarize all that, right, we don't want to deal with all that complexity right now. So to summarize all that, we just call it an effective diffusivity. So whenever we need the diffusivity of component A, we can just use this so-called effective diffusivity. And in fact, in other courses, you'll see that there are other generalizations that are also associated with this. For example, diffusing into pores of particles and so on. But anyway, for now, you can just think of this DAE as a way to say that's just the diffusivity of A that we have to worry about. Okay, so we've got A diffusing through the solvent to this particle where it is that reacting. So A is diffusing to the particle where it is consumed at a high rate. So it doesn't say anything about component B, it's just saying A is being consumed there. And, and we are told that at this position, right, 3 centimeters away from the center of the particle, we have the mole fraction of component A. So we are assuming there's some kind of point measurement that's happening. And you can see this point at 3 centimeters, it's outside of the particle, right? So the particle, well, that's diameter. So the particle itself has a radius of 1.25. And so 3 centimeters is some distance outside of the particle, right? And we have a measurement over there. So we want to know the molar flux of component A. Okay, so far, any questions or comments on the question itself? And so to answer this, let's just copy this and work through it in a separate document here. And let's do our little sketch as usual first. So we have this particle now. And this particle has this radius of 1.25 centimeters. And component A is diffusing from the bulk fluid towards this particle. Right, and we are told the reaction, how is it said here? We are told, yeah, it's consumed at a high rate. So when we see a term like this, right, high rate, we must always ask, what does that high mean, right? A relative term like high, that means something specific. And you'll see that's a recurring theme, right? Last time we also talked about some specific terms which turned out to have well, we had some terms which looked like they were just general things like stagnant and all of that, but those translate to very specific statements in our development. So it's consumed at a high rate. So that means the rate of consumption is high in comparison with, and the only other phenomenon happening is that A is diffusing. So this tells us that A is consumed much faster than it diffuses. In other words, as A reaches the particle, it immediately gets consumed. So what that tells us is that the concentration of A on the surface, or the mole fraction of A on the surface, is approximately 0. right? And it's a little bit of a contradictory thing because A is being consumed there. And typically for the reaction to happen, we can't have a zero concentration. If it's a zero concentration, then that means there's none of A there to react. But that's not true. If the concentration here is identically zero, then that would give us a high driving force for A to arrive at the surface. Maybe you could think of this as a kind of in discrete time steps, right? Imagine that initially A had a high concentration everywhere, then the reaction started happening, and then that depleted component A on the surface. So it depleted A on the surface, then that caused there to be a high gradient, right? If A on the surface is low compared with A out here, then that means A started, that concentration gradient would cause a high rate of diffusion. But then A diffused in, but then the moment A reaches the surface, it gets consumed again. So those two things are, if you like, competing with each other, right? The A is being consumed and that pushes the concentration down, but then that causes A also to diffuse towards the surface. And so that causes the concentration to go up. So A arriving at the surface is in conflict with A being consumed on the surface. And so we can say that A tends to zero, the concentration of A or the mole fraction of A tends to zero, but as it gets close to zero, more A arrives in. So you see all that discussion comes out of just saying something like it's consumed at a high rate, right? The moment you see a relative term like high rate, then you have to ask, well, high in comparison with what? And so it's in comparison with the diffusion flux. Okay, so that's one thing. So just from the fact it's consumed at a high rate, we now have this statement that on the surface, we can treat the mole fraction as zero, even though we know it's not exactly zero. And then the other fact is that at some distance from the particle, we have a mole fraction. So at some position out here, let's say this is well, we are told the position is 3 centimeters from the center. So there's 3 centimeters. And so at 3 centimeters, we have a mole fraction of 0.7 for A. And of course, that is then the radial the radial position 3 centimeters. So that means at any position around this particle at a distance of 3 centimeters, the mole fraction there is going to be 0.7. So we can see that there's a relatively high mole fraction or concentration of A out in the bulk here, and then A diffuses in towards the particle and the surface concentration is 0. Right, any questions or comments on any of that so far? Just letting people in. Okay, so that's the starting point. And then next, we have to look at, well, we are asked about the molar flux of component A. So, of course, we have our usual molar flux expression. And so we can write here that the molar flux of A is equal to minus C D A, and we are calling it E, the effective diffusivity, times del of XA. And we are going to just treat that as a dxa dr, right? And something that we have to consider here is that we are now talking about spherical coordinates, right? We are talking about radial distances from the center of the particle and so on. So we have here a coordinate system which is most appropriately spherical. So we are talking about r positions θ1 and θ2. Okay, so those are the variables of interest to us. And we are not told anything that leads us to believe there are gradients in the angular direction. So if we think about diffusion in this direction, right, with respect to the angles, whether it's on the plane like this, or I'm not sure if I can draw it well, but in the angle coming out of the page also, we are not told that there's anything special going on in terms of the angles around the particle. So if we assume that all the changes are happening in the radial direction only, then we can neglect these other directions. And we'll talk about this a bit more as we go on, that we always have to think in 3 dimensions. Whenever we are dealing with diffusion fluxes and things happening in the real world, right? The real world we are living in that we can observe, the physical real world as we think of it has 3 dimensions. And well, there's time as well. So we do deal with time and so on, but talking about the physical world, the 3 dimensions, whether if it's in Cartesian coordinates, right, in rectangular coordinates, then we talk about X, Y, Z. If we talk about spherical coordinates, then it's R, theta 1, theta 2. So here, it doesn't seem like there's anything interesting with respect to the angles. So we'll just deal with the radial position. Right. So when we write this now, here, we just write in terms of the radial position. So we know that's the first term, and then we have also XA, and it's NA plus NB. And in this case, our other fluxes are not given to us. We are only told about component A, and it's diffusing through a stagnant solvent. And we take that to mean that NB is approximately 0, right? So taking that NB is 0, then we can get rid of this, and we are left with just XANA. And so we can write, we can do the usual thing. We can take A across to the other side, and we write this as NA1 minus XA, and we've moved that term. Right, so that's the expression that we have now. And our tendency is to go ahead and integrate this equation as it is. And one of the things we said last time was, well, if our system is steady, right, if our concentration profile, right, we know there is a non-zero profile, right? We've got a high concentration of A here and a low concentration of A there. So we expect that A concentration is varying in some way. So the concentration is not uniform. The concentration is varying across the space, but it's at least steady. So if our concentration is steady, then that implies to us that there's no change in the number of moles of A as we look along the radial direction. So as we look along in R, the number of moles is not changing, right? The number of moles is different, right? If you take a slice here and you take an equal volume slice here, right? And the radial distance will be slightly smaller here because the area is a bit different, right? The surface area of an imaginary sphere. You can imagine, right, with equal volumes, if you've got higher concentrations here, the number of moles here is different to the number of moles there. So we know it's not uniform. The number of moles is changing, but in each subspace here, the number of moles is at least constant. And by the way, when I'm drawing those green lines like that, what I actually mean is that you can imagine a shell of a ball here, right? So you've got your particle on the inside. Here's our particle. And then we are imagining some radial position here. So some radial position, this is radial position R1. And then there's some other radial position here, R2. And think about a real ball, a ball in the real world, right? Not an, how can I say, not a ball, a theoretical ball with zero thickness, right? If you take a real ball, in the real world, that ball has a certain thickness, right? By thickness, I mean the wall of the ball, right? The wall of the ball has a certain thickness. So this is the wall of the ball. And so we can ask, what is the number of moles, right? What's the number of moles in the wall of the space? So we are imagining a position R1, we are imagining another position R2. And so between R1 and R2, there's a certain number of moles of A in that space. And so we are saying now that that number of moles there must be constant. So Na over there is constant in time. So if the number of moles in the space is constant, then that must also mean that the rate at which moles are entering here must equal the rate at which moles are leaving there. Okay, and now how do we write the moles leaving and entering? So the way we do that is to say dN A dt, so the number of moles of A changing with time between two positions. So let's say this as between positions R. See, yeah, R is an element of R1 and R2. So R is in, so for all R positions between R1 and R2, we have a certain total rate of change of moles. And the rate of change there is equal to the molar flux coming into that space. So the molar flux coming in, and this will be at position R1. And here we have to say times 4 pi R1 squared. Right, remember, this is the surface area of a sphere, and this is the molar flux on that sphere. So coming into that space between R1 and R2, coming in, we've got that flux. So that's the flux on that inside surface, and that's the area of that inside surface. And then leaving that that space, we have a flux on the outer face. So that's R2. So the molar flux at R2 times 4 pi R2 squared. And we know this is all steady. We know that it's not changing with time. So this is equal to 0. In other words, we can say that these fluxes, or well, these molar, I don't want to say flow rates, but these molar rates are equal. Right, so the molar rates are equal. We can see we can cancel by 4 pi on both sides. And we can see we are now weighted by R squared. And this is different to before. Before, when we had a simple rectangular coordinate system, then we could just say NA at Z1 equals NA at Z2, right? So before, we had a simpler expression. We said if the concentration is steady, then the molar flux is uniform. So we had said that if we are traveling along in a tube like this, and if we consider two positions here and here, just the fact that the concentration is constant there means that the number, the molar flux there equals the molar flux there. And that was fine, but that was also in a special case where the areas were identical. Remember, the cross-sectional area here is equal to the cross-sectional area there. So we don't have that situation anymore. Now we have two different radial positions, right? We are, maybe let's kind of make this bigger. Yep. So we have two radial positions. And so the area here, the area on the inside right? The space of interest is this space, right? We want to know the rate of change in that space. So the area on the inside of that space, that area is different to the area on the outside of that space. So if we want to say the number or the rate of change of moles in the space is constant, then that means the molar arrival rate here, the molar rate here must equal the molar rate there. And the molar rate is the molar flux times the area. And so we are saying here that these molar rates must be equal. And so this time we have to have the radial position squared in there as well. Any questions or comments on that? Okay, so that's what we actually have. And this is true of all radial positions, right? You see, if we are requiring that these two radial positions are equal, so we are saying this has the relationship with this, then you see we can write the same thing on all the radial positions. Right, let's do this a bit better. So we take one here, then we can take another one here. And so we can take as many radial positions as we want. And we'll always be saying that the molar rate coming in here, the molar rate coming in here must equal the molar rate leaving out here. And the molar rate leaving here is the same as the molar rate leaving there, right? It's across the same interface. And then we'll also end up with that molar rate must equal that molar rate. So we can draw as many of these concentric circles as we want, and we'll get that the molar rate is the same moving away like that. And so we can say, generally speaking, that all these molar rates can be referenced to, let's say we had some radial position, let's just call it R0. We don't know what R0 is yet, but we'll just say, we'll define some position R0 where we happen to know the flux. So that is the molar rate at some radial position. And then that must equal the molar rate at all radial positions. So if we pick any R, where R is outside of the particle, so we should specify here for R more than R, let's let capital R, where R is the particle radius. Right, so we have this expression now. We can say it's always going to be true that our molar flux will look like this. And so we can say then the molar flux at radial position R is equal to this stuff divided by this thing. So we can say the molar flux at position R is the molar flux at some other radial position multiplied by that radial position divided by R squared. Okay, so that's that gets us some way towards it. And now what we want to do is apply this in our balance here. Right, so we have this balance. So in terms of our flux equation, that's what we have. And so we are going to replace this NA now by this expression. And what we can do is say, let's work with this in terms of the surface radial position. So we want to know NA at R. So this is the flux on the surface of the particle. So this is going to be R squared, right? So now the expression looks like this. And yeah, what we have to do now is still integrate this. And so here, NA, this is NA at R. So this is a specific flux, right? Generally, NA is a radial position in R. And now we've created a function of R where this is a constant. This is the flux at a specific point, R naught. Maybe a better way to write this is N A naught like this, right? So NA naught is fixed with respect to R, right? If you think about it, that is the flux on the surface here. So that's NA naught. So when we talk about NA as a function of R, we are not considering all those other positions. We are talking about one fixed number. There exists some flux, some surface flux here. So that's our NA naught. So that's not changing in R. That's stuck on the surface. The fact that that NA changes with R has been accounted for by substituting here. By substituting NAR for this, we've isolated out a constant and we have a function in R here. So that R is there now. And then if we look at everything else here, these we said are constants. So XA and R are the only two variables, right? NA naught we said is constant. So what we can do now is separate the variables. And this time R we have to account for. So we can, let's see how best to do this. So I'm just going to write this as R squared here. And then I'm going to take my dr over R squared. dr over R squared, like that. And then, so we've taken out this dr, and then this XA, we do want to divide by XA here. And then we know all these are constants. So we can divide here as a constant. And by the way, that R, right, that's a constant, right? The variable lowercase r, that's a floating variable that moves in the radial position. R is the fixed radius of the particle. So that's a constant in R. So our differential equation looks a bit different now. And yeah, the difference is we now have the 1 over R squared there. So there's a bit of integration on this side as well now. So to do this integration, of course, the integral of 1 over R squared is going to be minus 1 over R, minus 1 over R. And this is between positions R0 and some R. So this is between R0 and some R. Right, and if you want to just check this, the derivative of 1 over R is minus 1 over R squared. So minus 1 over R squared is this 1 over R squared over here. So you can see the integral of 1 over R squared is minus 1 over R like this, right? And then we want to integrate the right-hand side as well. And so this is, of course, minus ln of 1 minus XA. And that's going to be between XA naught. So that's the mole fraction at position R naught. So that's XA naught. And at position R, we just defined it to be X sub A. Okay, so that's our expression now. We've got minuses on both sides, which we can cancel. And so that's our final expression. That tells us how X, we can take exponential. So if we divide this on that side and take the exponential, then you can get XA as a function of R. Any questions or comments on that so far? Right, so that's an expression that we have. We still actually are trying to get to the flux, right? We haven't calculated that yet. Let's just apply our n positions. So when we rewrite this, this is of course 1 minus R minus 1 over R0. And then this one is of course ln of 1 minus XA over 1 minus XA naught. And we are solving for NA naught down here. Now, we do have a value at a specific position. So in the question, we are given the mole fraction at 3 centimeters. So we do know at 3 centimeters, we have a mole fraction of 0.7. And the other thing we know is that on the surface, our mole fraction of A is approximately 0. So when we said the reaction rate is high, then we interpreted that as that the surface concentration is approximately 0. So we have 0 here and 0.7 there. The radial position here is 1.25, and the radial position here is 3 centimeters. So that then specifies everything we need here. So R is 3 centimeters and R naught is 1.25 centimeters. XA is 0.7 and XA naught is 0. So you can stick all those numbers in there. The effective diffusivity is given, the concentration is given, and the radius of the particle is given, again, 1.25 centimeters. So the only unknown now is NA naught. So we can simply solve this expression for NA naught. Does that cover it? Did you have any more questions on this question in the tutorial? Where is our originator of the question? Okay, so you see the development is largely the same. So all of that still applies. And the difference now is that our statement of the number of moles being steady, of the concentration profile being steady, that is in the spherical coordinate sense, that gives us a slightly different expression of the equality. So now we can't say the fluxes themselves are equal. Now the fluxes weighted by their areas are equal. And then that introduces a radial complication, which then needs to be accounted for. Okay, so that's question 4 there. And by the way, in the Publon, you've got this thing also. You've got that the reaction is also given to you here. So, sorry, 1 second. But can I have this, please? Okay, so, okay, fine. Sorry about that. Yeah, so we've got the reaction itself happening here. So in this problem that's given at the link I sent you, you have this reaction happening as well, and that will change your expression here. So instead of NB being 0, NB equals minus 2A. Let's just check that. You've got twice as much B forming as A. So you would say NB equals twice NA. And remember last time I said be very careful with writing it the right way around. Don't read this as Na equals 2 Nb, right? This means that you've got twice as much B as A. So Nb is Nb is 2 Na. So the 2 is on the other side. So Nb is 2 Na. And by the way, there's a minus sign here because they are in opposite directions. A is a reactant, it's diffusing towards the particle. B is the product, it's diffusing away from the particle. And so that's what we get. So your Na and Nb, in this case, it's not stagnant or equimolar. So this term doesn't vanish, and so you've got this expression that looks like this. The rest of the development is pretty much the same, right? We use the same approach here. We say the fluxes at some radial position is referenced to the flux on the surface in this way, and then you substitute all that in, and you can calculate your answer that way. Okay, any other questions on this thing? Right, then moving on to, you also wanted to look at question 2.
Wait, so what about B, part B of the question of question 4?
Okay, part B. Okay, so we are told the particle has that density, 700 kilograms per cubic meter, and you have 2 kilograms of the particles. So, so we want to know what's the total consumption. So what we are saying now is, well, that's what happens in just one particle. But what if we have a container loaded with these particles? So this is much more like a chemical engineering problem, right? You've got a whole bunch of particles, and maybe it's a catalyst particle, and that's why they are there. Sometimes they are just there to provide surface area for reaction, a kind of substrate for the reaction, but whatever the case, we know that it's reacting on the surface, right? So there's a certain number of particles that's in our container, and we are given the total mass of the particles in the container, and we are given the density. So we can use all this to work out the number of particles, right? Because we do have the size of the particle, so it's 2.5 centimeters. So we can say here, the number of particles, don't move this thing. So we can say the number of particles is equal to the mass of all the particles divided by the mass of one particle. Right, so this is this M in the numerator is the total mass in the container, and MP is the mass of one particle. So the mass divided by the mass of one particle, and the one particle is going to have, so each particle has density rho, and then the density times the volume of the particle. So in spherical coordinates, or for a sphere, your volume is 4/3 pi r cubed, right? And well, we used capital R for the radius, and we know the radius is 1.25 centimeters, or 1 times 10 to the minus 2 meters, right? So I always work in SI units, as I said. We are given the density, so rho is 700 kilograms per cubic meter. And then if you have a check there, you can see that's all SI units, right? Of course, mass is kilograms. So the density is known, and then the mass that we are given is, what is it, 2 kilograms, right? 2 kilograms of particles. So we have everything that we need to estimate the number of particles in the reactor. Then we can say the total consumption rate of component A. So let's write it as dNA, dt. So that's the total consumption rate of A in the whole container. That consumption rate must equal the molar flux of A. So we know A diffuses towards the particle where it gets consumed. So we can simply take Na naught, so the surface flux, that's going to be equal to the consumption rate, that times the surface the surface area. So the surface area of a sphere is 4 pi r squared. So that's for a single particle. And then we want to multiply that by the total number of particles, which we've just worked out over here. So we've got the total number of particles. We know the radius of the particle, and we've said we can work out Na naught. So Na naught, we said we just solve for it from this expression. And that's basically it. There's a question on the chat for 4A, what's the value of R? So R is the radius of the particle, which we said was 1.25 centimeters. Let's just check.
Excuse me, sir.
Yep.
So I just want to check real quickly. Can you please go back to that page where you were doing the question? Yeah, right here. So you see that part, that equation which you wrote, 1 over R minus 1 over R naught. So what exactly is that R and R naught value? Is the R value, is it also 2.5? Is that one 2.5 centimeters, and R naught is that 2.5 centimeters plus 3.5 centimeters?
Well, when we were talking about this, we said this, let's see, where did we start saying it? So let's say at this point, we said at this stage that we may have some reference point, right? So at this stage, we hadn't defined anything. We said, this is generally true of any two radial positions. So if we just pick some arbitrary radial position R naught, then we can relate the flux at position R using this expression, right? So at this stage, it was general, and in this equation, it's just written in the most general form. And then if we want to look at a specific relationship, like the ones given in the problem, we are given only two facts. We are given a specific position, 3 centimeters, and we are told it's a high rate. So a suitable choice for the two a suitable choice would be R would be 3 centimeters, and R naught will be the radius. And so XA is 0.7 and XA naught is 0. So this is just very general between any 2 points. But when we write it in this form, we normally like to think of an R naught as some starting position. You know, the 0 kind of implies a starting position. So a suitable starting position will be the radius of the particle. So another way we can think of this is as a capital R here, as our radius of the particle. And then we would normally write this as a surface. So yeah, the surface mole fraction of A. That cover it?
Okay, thank you, sir.
Thanks. Okay, and Hanifa, does that also answer your question there? Okay, I guess. Okay, thanks. Okay, any other questions or comments on that? Okay, then in question 2. So like I said, use this correlation and your molar mass, and let's see your molar masses. So you just look up the molar masses for hydrogen and nitrogen. You are given the pressure and the temperature, and then you want to look up for this correlation what the units are supposed to be for all those things. Then your omicron, you look up in this table. So that's, of course, your collision integral. So you have to calculate this kappa T over epsilon. And for that, you have available your Leonard-Jones force constants. So you've got epsilon over K here. So you just look up for each of your components, what those are, and then you use that in your expression. And then from that, you can look up your collision integral. And then there's the averaging. So just check, I think it's shown in detail in the textbook, the averaging for Omicron. I think that one is a simple linear averaging for the two species, but just have a look at it. And then also for your sigma, you just look up sigma. It's on the same table as your Leonard-Jones constants. So you get your sigma here, and then you average that as well. I think that one is more of a geometric averaging. So just look in your Welty-Wicks and Wilson at this example. And then, so you get the mean values for those two. Everything else is specified, and then you can calculate the diffusivity there. Were there any questions? Yeah.
So really quickly, you said we had to calculate that ohm D value and stuff, and we have to use, but first we have to calculate that KT over epsilon. So we first, I just want to make sure this is how you calculate. So first you find whatever, you find epsilon A over K, you take that value and then you divide it, and then you divide that value by the temperature which is given to you.
Yeah, or you divide temperature by that value, yeah. And then you'll get KT over epsilon.
Okay.
Yeah, so it's T divided by this thing that will give you this one. And then you look it up there.
Okay.
Yeah. Any other questions or comments on that one? All right, then looking at what we want to cover today. So hopefully that gives you some experience with the molar flux and diffusivity and all that. And there are some case studies that are outlined here. So in the Dropbox folder, you'll find these case studies. So these are 4 nice questions, which you won't be able to work through as yet. But I'd like to establish these 4 questions as a kind of nice framework. And as we develop more theory, we'll be able to address each of these questions. And maybe we can just outline what these questions are and just see about kind of appreciating the question first. So, well, actually this one, this is a straightforward, okay, I'm just looking for, okay, so think about something like this. We've got flow in a cylindrical tube fed with a stream, and so we are given the entering concentration, and then the fluid is perfectly mixed in the radial direction, but due to axial competition between convection and diffusion, concentration is changing. So we want to develop the concentration profile. Okay, so these problems, okay, what I want to do then is just describe some problems here, and then we'll work through them further as we go. So think about a problem like this, right? You've got a tube. So you've got flow in a tube here, and our component A enters, and there's reaction happening on the surface of the tube. So A is transferring down the tube, and if there was no reaction, then you can imagine the concentration of A will just stay constant. So it enters at a certain concentration, and the concentration will stay fixed. But if there is reaction happening on the surface of the tube, then the concentration is going to change as we transfer down the tube. So you can imagine when you just entered the tube, component A hasn't had any time to react on the wall as yet, so the concentration is still high. And in fact, because the concentration is high, the reaction rate will also be high, right? Because reaction rate is proportional to concentration as well. So it's high there. But then as we go further into the tube, the concentration is going to drop. So if it were just reaction alone, the concentration of A will drop like that. In addition to that, we do have that A is trying to diffuse as well, right? So just by virtue of the fact that we've got a different concentration between, let's say, this point and this point, then A will also tend to diffuse in this direction. So A is diffusing in this direction as well. And then in addition to that, A is just flowing through the system. So we've got A entering, so you can imagine a certain convective flux of A entering here and A leaving there. So if you like, there are three competing influences that can change the concentration of A here. So this curve that we drew without thinking, this curve is affected by all three things, right? And another thing to think about is that, well, the reaction is only happening at the surface here. It's not happening at the interior points of the fluid. So it's not completely clear to us as yet how we are going to account for that, right? We'd like to write a nice balance here, and it seems natural to us. We know A is reacting, we would include a reaction term also, but we can see we can't really do that, because if we are writing a balance on this little box here, where the reaction is not happening, it's not legal, if you like. It's not valid to write a reaction term here also. So that's what we are trying to move towards. We want to be able to understand how we can write a rigorous balance here. We want to be able to write a balance even on a sub volume like this. So we want to be able to understand everything that happens in a sub volume like that, or even a smaller sub volume over here, maybe a sub volume that's connected to the surface there. And of course, as chemical engineers who want to know what's the overall rate of reaction in this tube, we want maybe to write a balance on a volume like that. So those seem like very sophisticated requirements in the face of quite a lot of complexity. So we are going to try to build up each expression of each phenomenon and then move towards being able to answer questions like that. Okay, any questions or comments on that? And in fact, there are other types of problem as well. We could also think about the same particle problem. What if the fluid were flowing past the particle as well? In fact, there are some important practical case studies where there are such large pores that there is flow through the pore in the particle also. So you might have flow past the pore, and you might have all kinds of other gradients. What if the temperature was changing across the space also? So those are the problems we are moving towards solving now. And one of the things that we do to simplify the development is make certain approximations. And that brings us to this topic of film theory. And so some of you have asked about that mass transfer coefficient. So that's will emerge in the context of film theory now. So in film theory, we are acknowledging that our concentration is changing across space, right? That in a way seems obvious to us now. So let's just redraw this. So we know that if you have any concentration change, then we are going to see a transfer. And let's return to that very first drawing that we had. So we had a membrane, and we had two cells, and we had two concentrations. So we said this was a permeable membrane. So component A can diffuse across this membrane. So A can diffuse. And we've got a certain concentration here. So let's say we have a high concentration here, high concentration of A on this side, and a low concentration of A on the other side. So in film theory, what we say is, well, we know that there is a continuous concentration variation. So if we were to draw it, for example, we could say, well, the concentration is high here, and then it changes across the interface, and then it's lower here. Right, so we can start out with that. We know this is happening. And in film theory, we say, yes, fine, that's happening. But actually, if you think about your system here, you have such a small region where this concentration difference occurs that you might as well try and isolate out a subspace where all of that happens. And in fact, I want to exaggerate the situation. Let's add stirrers here. So let's say each cell is well stirred. So we are trying to keep the concentration about the same in each case. So if that's true, then our concentration difference is even smaller. So we can imagine then that our concentration, if it's approximately the same on this side everywhere, then we will have one approximately steady, not steady, one approximately uniform concentration here, and then another approximately uniform concentration down here. And then it's still the case that A is going to diffuse across this permeable membrane. And because the concentration is low on the right side, the concentration of A will start dropping near the interface. And I just want to put the interface points down here also. Let's do it carefully. So there's the one interface. That's one side of the interface. And here's the other side. So what will happen is, near the interface, we will have A diffusing to the other cell. So we'll get a certain drop at the interface. And then we'll have a certain other drop across the membrane itself. So there'll be a certain change of concentration in the membrane. And then we will also have near the interface, we'll have the usual, there will be a high concentration on this side, and that will go into the other cell. Right, so across this cell, it's also approximately constant, but near the interface, there are some changes. I did deliberately draw this with a discontinuous jump. You can see you've got some concentration of A here, which is different to the concentration of A here. And this concentration is not the same as this concentration. And the reason I'm doing that is this is a different medium, if you like, right? This membrane, think of it as maybe it's like a kind of a polymer, some kind of plastic. And so generally speaking, if this is a liquid, let's say, you've got a liquid and a plastic, and then your component A is going to enter that polymer, and that polymer will tolerate a certain amount of A in it. And so there's a certain limit. And in fact, I'm saying all this as if it's a foreign concept, but you are well familiar with this, right? In your thermodynamics course in ENCH2 TD, you are well familiar with vapor-liquid equilibrium. So between a liquid and a gas, there is a discontinuous jump. So if you just think about a liquid here, so let's say you've got some liquid surface, and then you've got some gas out here. We know that your gas fine near the surface, if let's say the concentration of A here is high, so near the surface you will have a higher concentration than in the bulk. That's all fine, but there will be a discontinuous jump in the concentration between the concentration in the liquid and the gas. Right across this interface, at the position of the interface, to the immediately above and immediately below, there are two different concentrations, just because different phases, right? In the gas, you can't tolerate concentration or densities on the order of hundreds of kilograms per cubic meter. Right, in the gas, you are on the order of 1 kilogram per cubic meter. In the liquid, you are on the order of hundreds of kilograms per cubic meter. So there is necessarily a discontinuous jump across a phase. So we can think of this polymer as being a different phase to the two liquids on either side. So that justifies the discontinuous jump there. But if you look in the phase itself, then there should be a continuous change over there, right? And the film theory refers specifically to the phase itself. So when we are talking about film, we are talking about the film here. So you can talk about one film here. I just want to draw that a bit more like that. And then there's another film here. So by film, we can think of it as the region where most of the concentration difference resides, right? If you are looking further in here, you can see the concentration is not changing much over here. So we'd rather just lump everything here. We don't want to think about concentration variations here where there are none. So we want to say, well, all the concentration difference on the cell on the right is in this red box here. And similarly on the left, there's no real difference across here. All the difference is concentrated in this zone here. And the difficulty with this is there's no clear position for us to talk about, right? In principle, the concentration difference is indeed continuous. The concentration always changes. But we set a simple criterion of 0.99. So we say, where is the point? What's the position where the mole fraction in our fluid achieves 99% of the bulk value? So if you take an infinite distance down this way, you could identify a certain mole fraction here. Let's say the mole fraction of A was 0.8. Then you ask, where is the position where the mole fraction is 0.99 times 0.8? And so maybe even if this tube is, or the cell is 20 meters long, still you might find that 0.99 of that bulk value only falls in 1 millimeter. That's quite often the extent of the concentration difference. So it's on the order of millimeters. So your concentration might only be changing within 1 millimeter down this 20-meter cell. So we don't want to do the bother of doing the calculations all the way down 20 meters. We want to concentrate on where it's happening. So in the 1 millimeter, right, and I'm just saying 1 millimeter, right? Obviously it changes from case to case, but it's on that order, right? So we look up where is it 99% of the bulk value, and that defines for us the film thickness. So the same on both sides there. Any questions on that?
Sorry, sir.
Yes.
Sir, could you please repeat what, can you please explain what film theory is again?
Okay, let's, maybe the way to do it is to use some symbols and write out what we said there. So let's just copy this through. So here is our drawing. And we are going to say that there exists, let's define Z in this direction, right? So we can say CA, the concentration, or let's say mole fraction, that's what we've been talking about. So the mole fraction is a function of Z. in general. However, in a certain range. So let Z equals Z interface minus be the Z position at the interface immediately to the left of the interface, and let Z I plus be the position just to the right of that. Then we can say in a small zone, it's Z in the range of Z I plus. Oh, let's talk about the one to the left first. So Z I plus minus delta, oops, lowercase delta, and Z I minus all the variations in concentration are represented. Sorry, 1 second. I'm just going to ask for the background noise to go down. Sorry about that. Okay. So, so in this zone, look at this carefully. We are saying just to the left, and in fact, I've got it the wrong way around. No, it's right. So this is saying if we are looking at Zi minus, right? So we are looking just at this position here, that's Zi minus. Then just to the left of that is where all the concentration difference is concentrated. So the other side of here, so the left face of this red box, we are going to define that to be the position that's delta units to the left of that. So this delta, right, this is a lowercase Greek delta, that we define to be the thickness of the film, right? Remember, we said this red box is the film. And so let's define the thickness of the film to be delta. So the position here is going to be Zi minus minus delta. That gets us to this position. And then this is the position Zi minus. So between those two positions, all your variation in concentration occurs, right? So most of the change happens there. And you can see on the left face here, the concentration or the mole fraction there, let's write it here. So we can say XA at position Z equals, and the left face position is this one. The left face position is that. So at that position, our concentration will be 0.99 times the bulk concentration in the first cell. So it's XA in the bulk in the first cell, right? So there's the first cell. There exists some bulk concentration in here. So maybe that's 0.8. So that 0.8 times 0.99, you can see here on the left face of this, we are very close to being at the bulk mole fraction, right? So there's your bulk mole fraction, and we are very close to the bulk mole fraction at this point. So at that position, at Z equals Zi minus minus delta, at that position, we are at 99% of the bulk value. And then we've got some other value on the other side over here. So for that side, we'll just we don't have a strict definition for that, so we can just call that XA at the interface on the minus side. And of course, you can do the same on the other side. And I'm just going to copy, paste, and update it here. So on the other side, we are looking between positions Z, I plus, and this one will be plus. And now what we have to do is specify a different form. So on the other side, we'll call it delta 2. We should have used delta 1 on the left side, but let's just say that delta without anything is the left side thickness. So now we are looking between the interface on the plus side and a small distance inside, which is delta 2. And so this here we are saying that at xi plus delta, we are far enough inside of the bulk there that we are at 99% of the bulk value, and that's on that side. Okay, and then at the interface itself, then we are at some other value, which is xi. So I don't know if defining things helps with that. Does that? So any further questions or comments on that one? So always it helps to just recall what we are saying in form theory is that all the concentration difference is concentrated into a small zone. And we define the thickness of that zone to be delta. And we don't know offhand how thick that is. There's no number that we can point to and say, the delta is always 1 millimeter. The thickness of this form does depend on other factors, like how fast we are stirring the cell, right? The faster you stir the cell, the more homogenized it is. And so the smaller will be the zone, right? As you increase the speed here, this thickness will get thinner and thinner. Sorry, just 1 second. Let's take. I just need to check something. Hi, so sorry about that. Yeah, there's a bit of repair stuff going on. I'm actually locked in because there's a gate issue, but someone came to repair it. So that's where I was. Okay, so using that notation, hopefully that clarifies things. So we were saying what helps is just to take a step back. A film, just think of a film. And a film, in this case, it's an imaginary thing. As we were saying, as you increase the rate of rotation on your impeller, if you put more energy into mixing here, then this film will shrink further. It won't go to 0 because you do have concentration differences across the space. And so there will necessarily be some space needed for nature to catch up to and try to equalize and balance out these concentration differences. But still, as you apply more mixing, you can reduce the size of that. Another thing to remember, of course, is that this is a theoretical view of things, right? A film is an imaginary thing. We are only creating a film in our minds because it's going to make the calculations easier. In nature, there's no such thing as a film. In nature, there are concentration gradients and concentration differences, but just in our view of it, in the way that we are looking at it, we are defining a position where most of the inside of which there is most of the concentration change happening. Shall we go through that again? Any further questions or comments on that? Okay, and before we go further with that, I see there's a question in the chat about the units of this equation. So can you just mention which equation you are referring to there? So question 2's equation. So the units of which quantity? So I guess that's of diffusivity, right? So there's a question about the units of diffusivity, I think. So towards that, to answer, what are the units of diffusivity? Let's write that Na equals d diffusivity, and let's use that effective diffusivity. So molar flux equals diffusivity times dCA dz. And if you look at this, your left-hand side, on the left-hand side, you have units of moles per second. This way, moles per second, and this is per area, so per meter squared, So that's on the left-hand side, right? You agree, these are the units of molar flux, right? There's molar rate, moles per second, and then it's a flux, so per area, per square meter. And then we want to know the units of DAE, and then we've got DC, DZ. So the units here, concentration, of course, that's moles per cubic meter. And you've got DZ, so that's meters. So overall, this is moles. This is going to be moles per meter to the 4. So moles per meter to the 4 here. And then if you just compare left and right, you can see what's missing is per second. So that's per second was missing. Moles, that's fine. And then in terms of meters, you've got an extra 2 on this side. So we need here meters squared. So the units for diffusivity are meters squared per second. So I'm not sure whether that's what you were asking about, or whether when I said the units in the correlation. So just check in your textbook, the correlation, and there are some worked examples. Those show you all the units there. I think what I'll do next time is I'll bring that example and we can talk through that, since there seem to be a couple of questions on that. Okay. Then coming back to this here, so that's the film theory, right? We, in a sense, we haven't done anything new here. All we've done is define a region that we hope is going to make things easier for us. We've just defined a certain thickness, delta, and we claim that all the, or we define it to be, we don't have to claim anything. We are just defining it to be the thickness in which our concentration reaches 99% of the bulk value. And then we think we'd be able to use that to simplify our equations later. So that's what we've got in terms of the definition so far. And then the thing we are actually going to use it to do is simplify our diffusivity. So what we are going to do is say, well, we know it's actually a curve. We know that the concentration is actually on a curve like this. But what if it was as simple as a nice straight line there? What if all our mass transfer, all our diffusivity, instead of having to integrate an exponential function like we've done a bit earlier, instead of having to do all that, let's just be engineers for a minute and let's just say, there's just a straight line there. I don't care. In this 1 millimeter, I'm not going to sit here and work out exponential functions. I'm just going to say, well, it's just 1 millimeter. Let's just draw a straight line and do it. And you see, that is, I'm saying it as if, as engineers, we have intellectual challenges, but, it is clever to make simplifying assumptions like this that simplify all the equations later, as we'll see. So that's what film theory is about. It's about making a nice approximation, which works quite well, right? In this 1 millimeter, it's quite a reasonable approximation to say, well, a straight line is good enough to approximate what's happening. So the way we do that is we say, well, your molar flux, Na, fine, it really looks like this, right? Your molar flux, I want to write it like this. Okay, let's write it in the concentration form. So strictly speaking, we should be saying this, right? Let's just say Z for now. However, I want to propose a much simpler form. I want to say, just make some constant, I'm going to call it Kc, times a concentration difference. And that's going to be the bulk value minus the interface value. Right, so this is strictly true. This part is what we know is strictly true. This is the most rigorous way to do it. But as engineers, we want to go with a simpler view of it. And we want to say, I just want to multiply some constant, some fudge factor, by some concentration difference. I know that the molar flux does depend on concentration differences, but I'm not going to bother working out every single concentration at every single point when it's just 1 millimeter and I care about just this point and this point. So I'm just going to take these two endpoints, work out the concentration difference there, and then multiply it by some constant. I'm just going to define it as K. I don't care whether or not in physics you can find such a K. So as engineers, we've gone ahead and proposed this form, which will be nice and convenient for us. And then we say, well, we do have this theory available to us. So let's think about what's happening here. So if we were to think about, well, we are talking about the same thing. These are both the molar fluxes. So let's see if we were to apply our approximation to this side, if we were to say that it's approximately linear, then this Ca, right, that delta Ca we know is equal to that thing, right? It's equal to that. And then we have also said that all of this is happening in a specific thickness, which we defined to be delta. Right, so if we were to find some equivalence with our invented film theory in terms of the rigorous theory, which is this, the way to translate from the Fick's law into our film theory is by saying, well, the difference in concentration is the bulk minus the interface, and then the difference in the position is that thickness delta. So that's, if you like, our translated form of Fick's law. And then if you compare these two, right, we know these are both talking about the same thing. We are trying to approximate the same molar flux with this mass transfer form. So if that's what we have, right, those are equal, then we can see we can cancel this on both sides. So we can divide through by this difference. So we divide here, and then we've divided that out there. Then we can say that our, by the way, I should have made this a minus sign. We do want to keep the same direction. Right? So that minus is going to cancel there. So then we have a nice relationship between our invented constant and the rigorously defined ones, the diffusivity and the film thickness. So we can calculate Kc. We know DAE, we have the correlations to estimate DAE, and we've defined this delta. We know delta is a little bit complicated. We need to, that thickness changes as we change the mixing rate and all of that, but still we've at least defined it. So now we have a relationship. Okay, and if you look in the problem, and in fact, I think problem 2 does ask us to do this anyway. Yeah, so in problem 2, we are asking about the mass transfer coefficient. So what we have done in problem 2 is we have derived an expression to estimate the change in mole fraction as a function of position. So we've got this nice expression, and this is nice in general. We said we could use this for any 2 points R and R. And I know in the first part, or in the first 2 parts, we fixed these eventually. We said let R be at 3 centimeters and so on. So let's go back on that now and say, well, we have worked out NA0. We know that's the surface flux, and we know the surface mole fraction is 0. So all that is defined. So let's go back now and say, well, now I still have this nice general form. It doesn't matter that I once applied it to get one of the constants. It still applies. This equation is still valid. That means it still works for all radial positions and all mole fractions. So I can use the same equation to work out my film thickness. I can stick in here a value of 0.99 times the bulk value. So we are given some bulk value, multiply 0.99 by that, and then we can work all this out. NA0, it's the same surface flux that applies. It's the same surface mole fraction. So all this is known now. If I know I want 0.99, and now I can calculate the position at which I get 0.99 of the bulk value. And by the way, I think this was a pure A. No, it wasn't pure A. Well, anyway, just take it as pure A in that example. So this is simply 0.99. And then we can calculate R. So this tells us the radial position at which we get to the film value, the edge of the film. So we've got R now, and then R minus the radius, that's the thickness of the film around the particle. And that's basically it. So we go back to this nice general form, look up for the 0.99 mole fraction of the bulk. We look up the corresponding R value, and we can use that to work out the delta. So R minus big R, right? R minus big R. So we can say, we can write this as R where X A equals 0.99 X A bulk. It's a little bit too, it's a little bit, it's a bit notation heavy here, but anyway, that's maybe that, hopefully that makes it a bit better. So R at this specific position minus the radius of the particle, that's an indication of the thickness of the film. So all we need to do is take the diffusivity that we were given and divide it by the film thickness, and that will be a good estimate for the mass transfer coefficient. And then we can use a nice simpler form like this. Okay, any questions or comments on that? Okay, if not, that was basically what I wanted to cover today. There is another tutorial in the Dropbox folder. So where are we here? So this one takes you a bit further through. So some of these, this is more like that reaction problem that we introduced earlier. And then this one has us thinking a bit more about diffusion through spaces and interacting with surfaces and so on. So see if you can derive an expression for the concentration as it varies across your particle. So that's your question 2 there. And then also look at deriving the expression across the through the radial positions as well. So another question in the chat about the recording. So yeah, I have started uploading those recordings, but I must say the concern for me is then that people don't interact properly in these sessions. And you know, what does help is when people ask questions during these sessions, because yeah, that's where I don't know what is what's not clear or what needs further elaboration. So I will slowly upload these things, slowly and reluctantly. I will keep uploading things, but please do continue interacting here and posting your questions so that we can have good sessions here. Okay,
Excuse me, sir.
Yes.
So just really quickly, I understand that there's a file on Dropbox which is under case studies, if I'm not mistaken, and it has all those example questions. Now, I know you said that we won't be able to do all those questions just yet, but is there any questions from there which we can look out, you know, just to go over? You know, for example, is there any questions from there which maybe we can look at and do?
Sure. So in fact, I thought this was something different to what it was. I do have another nice file which outlines some nice problems. These problems are simpler than what I had thought this was. So you can actually do this one. So it's consumed. Yeah, this you can do. This one relies a little bit on your fluid mechanics in second year. So what year is it? This is second year. So gravity-driven exit flows, you might need to look up some of these if you haven't covered that, but you can do this. This one is the 2-compartment cell. So in fact, this we have done already. And then this one, this is the one where we introduce the flow through the cylindrical tube. Here we don't have reaction. So this one is a bit simpler than what we introduced, but you can start working on this. And this one, so this one is a bit more like that reaction example. So the walls are permeable in this case. So here you are losing component A. So it's quite similar to that other drawing we did. And in fact, here you've got the full development given as well, right? So you can see the development of the expressions, that's part of what we do. So we are going to do these in quite a bit more detail as we go. So I don't know if I can say this effectively, but don't look at the solutions yet. Just work through these, just using what you know currently and see how far you can go with that. Okay, does that cover it, Sakim?
Yes, sir, that's fine. Thank you.
Okay, any other questions or comments there? Okay, if not, I guess that's it for today. Thanks and see you in the next one.